circular motion is everywhere, from like washing machines and cars and helicopters to the Earth itself, maybe the solar system. What about stars moving around a galaxy? It's actually one of the most common types of motion in the whole of existence, circular motion, and it's not that hard to deal with. From today, we're going to put our mechanics hat back on, and we are going to look at the very, very basics of motion in a circle. What are the rules? How do we get something to move in a circle? It's a really, really straightforward topic, but before we start, I want to help you get into the zone of mechanics. And so, dead simple starter for you to have a go at, remembering some of the key definitions from Module 3. This will take you right back. So let's take a look at the answers to those questions again. Why did I ask you about these? I asked about speed just because the very first equation that we're going to derive is your speed when you're moving in a circle. I asked about velocity because one of those two things is constant and the other one changes. Hopefully, as you can see, when you're moving in a circle, even if your speed is constant and you're moving through the same distance per unit time, your velocity will always be changing. Velocity has a direction, and therefore velocity is not constant, even though your speed might be. Calculating the average speed when you're moving in a circle is really straightforward. If you're moving in a circle of radius r, what distance do you travel? That's it. You travel around the circumference of the circle. And how do you calculate circumference? You use 2 pi r. So the distance that you travel is 2 pi r, the circumference of a circle, and that will take place in time t, let's say. So we can very, very easily come up with an equation for your average speed when you're moving in a circle. It's simply distance divided by time, 2 pi r divided by t. That equation is so fundamental and so basic that it doesn't actually appear in the book. So I would like you to find some blank space, be it on the summary page or maybe at the top of page 3, to write in v equals 2 pi r over t. And I would like you to label it 2 pi r is the circumference of the circle, the distance that you've travelled, and t is just the time it takes to travel that far. Hopefully, you'll think that that equation makes perfect sense now. From my experience, sometimes when people haven't heard about that equation, they get very, very scared because it's not what speed normally looks like. But when you've got it explained to you that way, circumference is distance, t is time, it's just speed equals distance over time, GCSE. Looking back to the starter again, I got you to define acceleration. Acceleration is the rate of change of velocity. Because your direction is always changing as you move around the circle, that means your velocity is always changing as you move around the circle. And therefore, you must be experiencing an acceleration because there's a rate of change of your velocity. That acceleration has to act towards the centre of the circle in order for it to work. And it can be calculated using the formula v squared over r. Acceleration is v squared over r. Remember that equation, you do not need to derive it because it comes from vector calculus. No. But the v in that equation is what I just told you. V is the circumference divided by time, 2 pi r over t. If you want to find the acceleration, it's that squared divided by the radius of your circle, and that always acts instantaneously at 90 degrees to your motion, that is towards the centre of the circle. If you put your thumb and finger at right angles like that and trace out a circle, your thumb and finger will always be at 90 degrees. It's the same as the relationship between the velocity and the acceleration. They're always at 90 degrees and the acceleration is always towards the centre of the circle. Those are the rules for circular motion. You can't change them, otherwise you're not moving in a circle. But Rob, I hear you say, in the starter we looked at Newton's second law, and Newton's second law says that wherever there is an acceleration or a change in momentum, there must be a force. Any object undergoing acceleration A would experience a force, F equals ma, and you're entirely correct. In order for that object to experience that centripetal acceleration towards the centre of the circle, it must also experience a force. This is called the centripetal force, and it is required for circular motion. The centripetal force is the resultant force acting perpendicular to motion, always instantaneously towards the centre of a circle. If A is v squared over r, then we very, very simply plug in the mass and use F equals ma. F equals ma, A equals v squared over r, and therefore F equals mv squared over r. It's not rocket science yet. Again, because the acceleration is towards the centre of the circle, the force is also towards the centre of the circle. Today we're going to look at the simplest possible situation where there's only one thing that could possibly be providing the centripetal force. But much like when you do F equals ma in general, F isn't really what you put into the equation. When you do a resultant force calculation, F is usually, tension minus weight or driving force minus drag. And so bear in mind when you see the equation F equals mv squared over r, it might not be an F that you use, it might be the actual forces themselves. This is mostly applicable in the next book when we look at motion in a vertical circle. Today we're just going to keep it simple and get used to using these basic equations. The centripetal force definition is it's the resultant force which acts perpendicular to the direction of motion instantaneously towards the centre of a circle. Acceleration, v squared over r, so force is mv squared over r. If those conditions are not met, you will not move in a circle. Simple as. When you're talking about circular motion, the notion of speed is only useful under certain conditions. If v is 2 pi r over t, then if I keep the time period the same and the radius increases, it means that the speed must go up. So for any object that's moving in a circle, like the second hand for a clock, maybe like a CD, different parts of that object are moving at different speeds. It would be really, really annoying if every time we wanted to know how fast the clock hands were moving or how fast my jet engine was turning, it would be really, really annoying if I had to always specify exactly what radius was required. There's a really, really handy quantity which removes this dependence on radius, and it simply looks at the angle turned through per second. This quantity is called angular velocity. All we're interested in is what angle is turned through per second. We use radians here. So for an object moving in a circle, the angle that we usually turn through is 2 pi. 2 pi radians in time t would give us an angular speed of 2 pi over t. It's that simple, Regular speed, linear speed is meters per second, so angular speed is radians per second. We give angular speed the symbol omega. If you're typing it, you can use W, but if you're writing it, use omega. 2 pi over t, angle divided by time. It's a lovely little measurement because it means that no matter how big my object, I know that I'm moving through the same angle per time. It also leads into a handy conversion. If I want to then convert that to regular speed, I can just multiply it by r. If omega is 2 pi over t, and v is 2 pi r over t, then the link between the two things is simply that V equals R times omega. Can you see that? That leads to one of the equations in the book. Just to help you consolidate angular speed, now this isn't the end of the video, just to help you consolidate angular speed, I want you to just try these 4 exercises. Try these for a moment first. Angular velocity of the second hand is 2 pi divided by 60 seconds, because that's how long it takes it to go around full circle. The angular velocity of the minute hand is 2 pi divided by 60 times 60 seconds, because that's how long that takes to go through a full circle. I know a few people sometimes get that mixed up. The Earth around its axis, this isn't a crazy question by the way, it takes 24 hours for the Earth to go around its axis, right? That's a day, that's what a day is. So if we use 24 times 60 times 60 as the time, that gives us the answer there. And the Earth around the Sun, that's a year. So again, just run the numbers, and it's very, very small. What you'll probably notice about all of these angular speeds is that they're quite small. And that is fine. Angular velocities are usually quite small values, especially if we're dealing with things that take a very long time, as in planetary motion. So we're used to it being a little on the small side. If you don't believe me that it's useful, try some of the questions in the back of the book and maybe it'll make sense for you. So just to summarise from this video, circular motion is very straightforward. The speed is the circumference divided by the time, 2 pi r divided by t. The acceleration must always act towards the centre of the circle, v squared over r. The centripetal force is the resultant force that always acts at right angles to the velocity instantaneously towards the centre of the circle. How do we calculate it? Well, we just use F equals ma and we generate F equals mv squared over r. The biggest new thing is angular velocity. Angular velocity is simply the angle divided by the time taken. You know, just in the same way that speed is distance over time, angular velocity, angular speed is angle divided by time. For moving a circle, the angle is 2 pi and the time is t. So angular velocity is 2 pi over t, which you'll notice is just a factor of r different from the actual speed. So if we take angular speed and we multiply it by r, we get the regular speed. Dead easy equations. So straight after this video, fill in the notes and practice. Something showed up in my assessment of the Waves books, and that was that we put in some very, very simple questions in an assessment, and about 10% of people could not do them. And I know that if those 10% of people just looked in the back of the book, they would absolutely kick themselves and feel very embarrassed, because the questions we picked were in the back of the book and they could not do them. Practice, learn how it all fits together. Email me, ask me any questions that you have, and I'll come back later in the week for number 2.